Okay, so in this video I'm going to introduce Euler's method, which is a numerical method for solving ODEs. In future videos I'm going to show other forms of the Euler's method, like the improved Euler's method and the implicit Euler's method. But for today I'm just going to show you the Euler's method. Okay, so today we're going to look at this ODE. It's very simple. Okay, so if we rewrite it like this, we see that it's a first order, linear, non-homogeneous ODE. Okay, so with this non-homogeneous term here, we know that if we find the complementary solution to this, to the homogeneous form of this equation, and we find the particular solution, and we add them together, that would give us the general solution. So I'm going to write that like this. Okay, so to find the homogeneous solution, we have to solve this equation, which is pretty simple to solve. It's separable, and the solution to this equation here is like this. Okay, it's pretty easy to do. You just separate it and integrate. I'm going to put these little subscripts here to show that that's the homogeneous solution. Or I should say the complementary solution to the homogeneous equation. And now to find for this particular case with this x over here, this non-homogeneous term, let us try a solution that looks like this, and we'll just plug this into this ODE. Okay, so when you do that and you differentiate it once, and you plug in y here, you end up with this. Okay, so to solve this, we equate coefficients, so we know that b must be equal to 1, and we know that b plus c must equal 0, so therefore c must equal -1. And so when we add together the solution to the homogeneous equation and the particular solution, we get this. And then when we plug in the initial conditions, which are over here, we get, when you plug in 0 for x, you get e to the 0 is 1. Plug in the 0 there, you get that. So that means that a must equal to 1. So our solution looks like this. Our exact solution looks like this. Okay, so let me just erase all this stuff here, because this video isn't to show how to solve a simple ODE like this. I just wanted to show you guys the exact solution, and then we're going to estimate it using Euler's method. So let me just erase. Okay, so we can see the exact solution. So I'm going to open up MATLAB right quick, and I'm going to plot that solution. Okay, so here's that solution. Here's the exact solution. You can see that initially when x is small, it looks like an exponential. But because it's e to the negative x, as x increases, that solution goes to 0, and the long-term behavior of the solution looks more like x to the -1, which is this linear portion of the graph that you see here. Okay, so I'm gonna try to sketch this in my notepad here. Okay, so our exact solution looks something like this. It's not perfect. Okay, so now how do we use Euler's method to solve something like this? For Euler's method, what you do is you discretize this derivative. Okay, so you can see here on the left-hand side of this equation that if you let h go to 0, then what you have here is this derivative. Okay, the limit as h goes to 0 is this guy here. That's like something you would learn in first semester calculus or in high school. But in this case, we're not going to take the limit as h approaches 0. We're going to let h take fixed values. Okay, so now if I multiply both sides by h and then add y sub n to both sides, we end up with something like this. This is Euler's method here. You can see that it makes sense. You can see that if we start at our initial condition, x is 0 and y is 0, you can see that we're going to march along the x-axis by increments of h. So we can set h to be as big or as small as we want to, and it's pretty obvious that the smaller h gets, the smaller your step sizes are along the axis, along the x-axis. So the more accurate your numerical approximation is going to be. Okay, so I think the best way to learn Euler's method is to just see an example of it in action. Okay, so first we start at a point that we know. We have this initial condition here. That says that x0 is 0 and y0 is 0. So let's plot that point on the graph. This is that point. So Euler's method says that our next y point is going to be equal to our previous y point, extend it out by what the derivative was at the previous point. Okay, so if that was confusing, I'm sorry. That's how I think about it, so let me show you what I mean. Okay, so this is the previous point. This is the point that we know. Okay, so if you look up at our differential equation, the derivative at x equals 0 and y equals 0 is 0. So that means that right here, this is the derivative at x and y equals 0 at this point along our graph. Okay, so somewhere along that line lies our next point. Okay, so let's find where that point is. You can see from this difference equation here that our x values along the x-axis are increasing by h. Okay, so let's pick a value for h. Let's say that h equals 0.5. So that means that at our first point, which is given by our initial condition, x equals 0, but then at our very next point, x equals the value at our previous point plus this step size. Okay, so in this case, since we're taking steps that are equal to 0.5, our next x value is right there. So like I said, our next x and y value is somewhere along this tangent line that's tangent to our function, and in this case, since the line is flat, we know that y is going to be equal to 0 and x is going to be equal to 0.5. So, and you can see that our next y value is going to be equal to 0 minus 0, which is 0. Our previous y value, which was 0, plus 0 is 0. Okay, so that means that that's our next point. And in fact, our x values increase by a half each time. So I can write our x values like that. And we just found our next y value, which is 0, so that's that point there. Okay, so now let's figure out where our next point is. Okay, so we know that it's somewhere along the line x equals 1, okay? But where what's our y value along that line? So we can find that here. So first, we find the derivative at the previous point, which is right here. So this is the point y equals 0 and x equals 0.5. Okay, so when y is 0 and x is 0.5, then the slope at that point is a half. Our next x and y coordinate is going to lie somewhere along this line. You can see how Euler's method sort of takes your last position and then extends it up based on the slope and then plots the next point somewhere along that line. So let's find out where that next point is. Okay, so we know that it's somewhere along the line x equals 1, okay, because we're taking step size equal to a half. But let's find out exactly where that point is right there, where these two, where this tangent line and this line x equals 1 intersect. So we look at this equation here. Okay, so we just said that this equals 0.5. Our step size equals 0.5. Our previous y value equals 0. Okay, so 0.5 times 0.5 equals a quarter. So that means that our next y value is equal to a quarter, which is right there. Okay, now let's see if we can find the next point. So like I said, at this point here, we want to find the derivative. We want to find the slope of this point. Okay, so this is the point x equals 1 and y equals 0.25. So from up here we can see that when x equals 1 and y equals 0.25, the slope is 3/4. So now, so that means that our next point, which is going to lie on the line x equals 1.5, which is going to intersect somewhere with this tangent line, somewhere right there. So let's find that point. Okay, so we said right here this was equal to 3/4. H is still 0.5, and our previous y value was 0.25. So you can see it, this is 1 over 2 times 3 over 4, so that's 3 over 8, plus 1 over 4, so that's 2, so that's 5 over 8, which is equal to 0.625. So you can see here that 6.25 is halfway between these two marks, and you know I didn't quite draw my tangent line perfect here, and this red line here, the exact solution, isn't drawn perfect either. So this point right here isn't supposed to be on the line of our exact solution. It's supposed to be a little bit below. But let me take you into MATLAB and show you how this looks. Okay, so here we are in MATLAB. You can see that I've set my step size to 0.5. I have our initial conditions here, and in the background I'm going to plot the curve for our exact solution. So when I run this script, you're going to see each point being plotted. Okay. So you can see, if you compare this to what we had, you can see that at x equals 0.5, we're at y equals 0. You can see that when x equals 1, we are at but y equals 0.25, which is what we have here. You can see that when x equals 1.5, we are a little bit above 0.5, and it actually equals 0.625, like I said here. And just for fun, I'll show you what happens with even smaller step sizes. You can see that our solution is very accurate with these smaller step sizes. Okay, so thank you very much for watching, and in my next video I will show you how to improve Euler's method with a method called, quite fittingly, the improved Euler's method. Thanks.